All right, guys, in the last video, we talked about this guy named Thompson, and we talked about the cathode ray studies that he did, and we talked about the neon gas study that he performed, which led him to visually see a neon 20 and a neon 22, which gave us this isotope term. So we're going to kind of venture on now. We need to get closer and closer to the discovery of the mass spectrometer. And it was actually Thompson's student. It was a student of Thompson that kind of led into the first MS instrument in a way. And this guy's name was Francis Aston. Now, Francis was basically based in Cambridge, and he studied not just neon 20 and neon 22, he took it on the step even further. So he kind of used that as a launching pad to go further with this concept of an isotope and things having different weights. So what are some of the things that he discovered during his time? Well, he focused on chlorine, and he found that chlorine had a 35 and chlorine had a 37. And he focused on bromine as well, and he saw that bromine had a 79 and bromine also had an 81. And he focused on krypton. See the trend? They're all noble gases here, or halogen family. They're kind of grouped all together. So krypton had a 78, or krypton had an 80, or krypton had an 82, or krypton had an 84, or krypton, yes, had an 86. That's what he focused on. He was proving Thompson's point over and over and over again. So there's got to be more to it. Again, this all leads to this whole concept of isotope that was now getting generally accepted by everyone. We have these isotopes that are around. We have these atoms. Sometimes these atoms are kind of normal. Sometimes the atoms ate a little too much and they're a little fatter. And we get different weights. So now we're going to tie it all back. And we're going to go back to that first video, and I said everything needs to have multiples of hydrogen, right? Everything typically was going to be a whole number when it concerns atomic weight, but it's not. Because what happens on the periodic table, and if your instructor did not tell you this at that time, I'm sorry. But the periodic table gives you the masses of the elements. So for instance, hydrogen is 1.01. That's what we've been using all along. Oxygen's kind of 16.00 if you rounded it off. But these numbers down here at the very bottom, these are not weights of the atom. Ta-da! Look what you've learned today. We've lied to you. They lied to you. I didn't, though. I would have told you the truth. But they lied to you. These are the masses of all of the isotopes that are averaged together. Because look at it here. We've got krypton. It can come to us in 78s. It can come to us in 80s. It can come to us in 82s and 84s and 86s. Which one do we put on the chart? Well, we know the abundance of each one. Of the 78, of the 80, of the 82. We know that percentage. So what we do is that we take the abundance of each one, we multiply it out, we add it all together, and that gives us what we call the atomic weight that is on the periodic table. That is why these numbers are not completely equal or even or whole numbers. Because sometimes when we take these averages, it's not going to be a whole number. It's going to be a rounded off number. So you are provided on the periodic table the average atomic weight of that particular atom. That does not mean that every single hydrogen weighs that much, or every single oxygen weighs that much, or every single krypton or bromine or chlorine weighs that much. That means that's the average weight. Whenever you see a chlorine come around, what is on the periodic table is the average weight of that atom. That is not the exact weights of all chlorine atoms put together. They all have isotopes, people. And Thomson's student, Ashton, was the one that was pushing and driving this narrative forward. When he was said and done, he discovered 212 isotopes. That's kind of his final number, 212. Right now, I think our number's at 270. So Aston was the one that discovered the majority of the isotopes that we still use today in a laboratory environment. Well, as you can imagine, 1918 comes around, and he eventually receives a Nobel Prize in chemistry. I'm going to say Peace Prize. He needs to be a Peace Prize, right? So a Nobel Prize in chemistry. So he made a little money off his research. He went down in history books off of his research. I think it was a pretty good gig. At the same time, 1918 was also a year that another man comes into play. And this guy's name was Arthur Dempster. 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 Arthur Dempster was playing off of this kind of mass spectrometer that Francis Aston was using. He knew that this mass spectrometer was separating things, and we were finding different weights of different kind of elements from the periodic table. And Arthur Dempster focused on uranium, and specifically uranium-235. This eventually led to the atomic bomb. So you can thank a mass spectrometer, because the mass spectrometer is what basically led to the whole concept of nuclear chemistry, uranium-235, isotopes, elemental breakdowns, and eventually the atomic bomb that goes boom. So mass spectrometry has played its role probably more significantly than any other instrument in our laboratory. So here's Francis Aston, British chemist and physicist. Kind of makes sense. I mean, we're playing around with charges. We're playing around with energy. We're playing around with a little bit of fundamental particle here. So that kind of goes hand in hand. Researched organic chemistry at his father's house. Give me a break. His work concerned optical properties, known as the polarimeter, and specifically tartaric acid, which is mainly found in wine. So he was a foodie, junkie, but thank him for the polarimeter as well. He kind of helped determine that. I mean, he's playing around with light beams, and he's sending light beams through a tunnel, and we're looking at what happens to the light beam. It's getting deflected. Well, the polarimeter, how does it work? We're shining a light beam through a tube that's filled with a sample, and the light is getting turned and rotated. So these things are very common. I mean, they go hand in hand. So Aston was kind of a part of that. Worked extensively with the fermentation of chemistry, leading to beer. Thank him for your beer. Every time you have that, maybe Bud Light, I hope not though, but every time you have that beer, you can thank Aston. He kind of helped push that narrative even more. Hobbies: car racer, skater, skier, mountain climber, photographer, astronomy, traveler, could play the piano, violin, and cello. Could you imagine that on a dating app? And he died at 68. He never was married. Don't know why. Rumors. But he never was married. All right, now we also talked about Dempster. So let's take a look at him. Here's Arthur Dempster, looking real scientifically, staring at his mass spectrometer right here. Canadian physicist. Taught physics at the University of Chicago. World War II, he worked on the Manhattan Project. I told you this led to the atomic bomb. What he can take credit for, though, is that he improved the technology that Aston was using. So Dempster took it, just like Aston did from his teacher, took it and expanded the knowledge. Dempster took that and expanded the knowledge. And he made a mass spectrometer that was over 100 times more accurate than the leading MS at the time. He was also chief physicist of what they called the metallurgical laboratory, Met Lab. Notice this is not Meth Lab, it is Met Lab, which studied the materials to make atomic bombs. Thank you, Mr. Dempster, for giving us that bomb that caused such devastation and chaos. So 1886 to 1950s, that's kind of where we've been led to at this point. Passed away at 64. Okay, so now this leads us up to the actual instrument itself. So a little bit of background about how we got here, a little bit about who played significant roles in this development and what we were learning from it at the time. And now we need to turn our focus to the basics, the theory. Now that we have this mass spectrometer, now that we know that this MS system has given people data on what we would call isotopes or fat little atoms, what can we do with it in our laboratory and how does it actually work? And of course, we've made improvements on it since the time of Dempster. This instrument has gotten better and better and better. And quite honestly, it wasn't until recently, and when I say recently, I'm talking about like the 80s and 90s, that people felt comfortable using the mass spectrometers in their own laboratories just because they thought it was a fringe instrument that was going on. No one really had full training on it. No one knew how it worked or how it operated or how to analyze the data from it. And now it really is commonplace. It seems like every instrument that we are putting in labs nowadays have a mass spectroscopy component, or at least they have the capability of doing it. So now it's more and more common, right? The same thing would happen with a phone. Think about it. Back in the day, phones did not exist. Then we got phones and they were corded. And then we got phones that were in our cars. And then we got phones that are fully cellular phones that are portable that we can take everywhere we want. Now it is commonplace. But years ago it wasn't. It was something completely different. Technology changes. So did the mass spec field. So what we're going to do in the next video is we're going to focus now on pieces and parts of the theory about how this instrument does its job and what it's doing to compounds as they enter.